Problem 3.2. Air at 30 degrees Celsius flows with a velocity of 2.8 meter per second over a flat plate, 1000 mm length, 600 mm width, 25 mm thickness. The top surface of the plate is maintained at 90 degrees Celsius. If the thermal conductivity of the plate material is 25 watt per meter degrees Celsius, calculate point number 1, heat lost by the plate. Number 2, bottom temperature of the plate for steady state conditions. In order to solve this problem, let us first draw the schematic. So as you can see in the diagram, there is a flat plate over which air is flowing. Let's say free stream velocity of the air is u infinity and its temperature is T infinity and convective heat transfer coefficient is H. Let's say the top surface of the temperature is represented by T suffix St and bottom temperature is represented by TSB. Let's say length of this plate is represented by L in the direction of flow and width is W and height is H. It is mentioned in the problem, surface temperature of the plate is greater than air temperature. So heat transfer will take place from surface plate to the air at the rate Q. So this is the complete schematic of this air flow over a flat plate. After drawing this schematic, let us enlist all the given things. So very first thing in the problem given to us is top surface temperature of the plate is given as 90 degrees Celsius. Air temperature is given as 30 degrees Celsius. Velocity is given as 2.8 meter per second. Length of the plate is given as 100 mm. So it will become 1 meter. Width is given as 600 mm. So it will become 0.6 meter and height is given as 25 mm. So in meter it will be 0.025 meter. Apart from this, we have been given the thermal conductivity of the plate material. And this is given as 25 watt per meter degree Celsius. So let's say thermal conductivity of this plate material is Kb. After enlisting all the given parameters, let us state assumptions. Step number 3 in the solution of forced convection problem. So assumption number 1 will be one-dimensional steady-state heat transfer. Assumption number 2 will be no heat transfer due to radiation. We are considering purely heat transfer by convection only. Point assumption number 3, constant properties of the fluid. Constant properties of the fluid. And assumption number 4, we are assuming air as an ideal gas. So all the gas laws will be applicable if required. One more thing, we are assuming the air is flowing along the length of the plate. That is, L is equal to 1 meter. It is not mentioned in the problem whether the air is flowing along the length or width or height, and this parameter is very important because the direction of air flow along that particular dimension will help me to select characteristics length. So that is why I am assuming air flow is taking place along the length of the plate. After stating assumption, step number 4 is to identify reference temperature. So how to select the reference temperature? So as you can see in the given problem, the flow of air is taking place over a flat plate. So it is an external flow, and whenever external flow is taking place, we consider mean film temperature as reference temperature by thumb rule. So since air flow is taking place over a flat plate, that is, it is an external flow, hence taking mean film temperature as reference temperature. And what is mean film temperature? I will represent it by T suffix f. It is nothing but Ts plus T infinity over 2. Ts is 90 degrees Celsius. T infinity is 30 degrees Celsius. So mean film temperature Tf will come out 60 degrees Celsius. So the reference temperature for the given flow is mean film temperature as 60 degrees Celsius. Step number 5, obtain thermophysical properties of fluid. And the fluid is air in this case. So how will I find the thermophysical properties? At Tf is equal to 60 degrees Celsius from heat transfer data book by C.P. Kothayndaraman. and page number 34. Okay, so from page number 34 of heat transfer data book by CP Kothandaraman, we can find out all the thermophysical properties. So what are these? So this is the page number 34. Properties values of gases at 1 atmospheric pressure. So for 60 degrees Celsius, as you can see here, I can find out the thermophysical properties. So as you can see here, at 60 degrees Celsius, these are the thermophysical properties we are supposed to find out. So rho, mu, this is alpha, nu, Prandtl number, Cp and K. Rho, mu, alpha, Prandtl number, Cp and K. So let us find out all these properties in list all these properties at reference temperature of 60 degrees Celsius. So the value of rho is 1.060 kg per meter cube. Then value of mu is 20.10 into 10 to the power minus 6. Newton second per meter square. Then comes nu. (18.97 into 10 to the power minus 6). Then comes thermal diffusivity alpha, (27.194 into 10 to the power minus 6). Meter square per second. Then Prandtl number 0.696 and Cp is 1005. Joule per kg Kelvin, and finally the thermal conductivity of fluid, that is air, is 0.02896. Watt per meter Kelvin. Now mind well, here two thermal conductivity values are given. One is for material of the plate, that is Kp, another is for fluid, that is air. So these are the thermophysical properties we could enlist from the heat transfer data book at the reference temperature of 60 degrees Celsius. Next one is identification of boundary conditions. So it is clearly mentioned the temperature of the surface of the plate over which airflow is taking place is 90 degrees Celsius. So the given boundary condition is constant wall temperature. After identifying boundary condition, step number 7 is nature of flow. So flow is taking place over the flat plate along the length. So I can calculate Reynolds number as Re suffix L as rho into U infinity into Lc over mu, or U infinity into Lc over nu. Here Lc is characteristics length will be equal to L for plate. Okay. The characteristics length will be the dimension in the direction of flow, that is linear dimension, and it is length of plate. So I can calculate REL equal to, I am selecting this formula, U infinity is 2.8, L is 1, and the value of nu is 18.97 into 10 to the power minus 6. So Reynolds number comes out 1.480 into 10 to the power 5. So the value of Reynolds number is less than 5 into 10 to the power 5 for plate, hence flow is laminar. So the flow of air over this flat plate is laminar. So the velocity boundary layer will be in the laminar region. This is the length of the flat plate over which the flow is taking place. So velocity boundary layer formation will take place, and that will be in laminar region. Now after identification of the laminar flow, now let us find out the value of Nusselt number and H. Okay. Now how to find out the value of Nusselt number? Actually there is a relationship between Nusselt number. Nusselt number is equal to H into Nc by K, where once again Nc will be L. So NuL will be equal to H into L over K, and this K thermal conductivity is the thermal conductivity of fluid, Kf. Now since I am interested in average convective heat transfer coefficient, So under such condition, average Nusselt number will be H bar into L over Kf. So if I could find out the value of this average Nusselt number, I know the value of L, I know the value of Kf, I can get the value of average heat transfer coefficient H. Okay. So once again, from heat transfer data book by C.B. Kothadaraman. Now, how to select the appropriate correlation for Nusselt number? So, once again, refer the data book and page number 113. So, this is for external flow. Now, here the formulae are given for laminar flow, as you can see here. And the formulae are also given for turbulent flow. So how to select the appropriate correlation of Nusselt number? So for that, first we have to identify type of flow. So in our case, the flow is laminar. Okay. So all the formulae will be 1.0 laminar flow category. Then our boundary condition is constant wall temperature. Okay. So one such formula is there, 1.1. But NUX is a local Nusselt number. This one. This NUX is local Nusselt number and it is of no use to us. We are interested in average Nusselt number. So there is a relationship between, as you can see here, average Nusselt number is equal to twice of local Nusselt number over the distance of NUL. So from this I can find out average Nusselt number for the length L is equal to twice of NUL. And from where I have got this formula? This is equation 1.3 and page number 114. So page number 114 and equation 1.3. Okay. But once again, how to find out the value of this NUL? So NUL is nothing but local Nusselt number for the flow of air over the length L. So how to find out this local Nusselt number? One such formula we have come across for constant wall temperature boundary condition. The NUX, that is local Nusselt number when air is flowing over a distance x, is NUX is equal to 0.332 REX raised to power 0.5 into Prandtl number power 0.33. So this I can select because it is in the laminar flow for constant wall temperature boundary condition. So all the conditions are satisfied. So now I can select NUX will be equal to 0.332 REX raised 0.5 PR raised 0.333. And from where I have got, this is equation 1.1 and page number 103. Okay. So equation 1.1 and page number 113. But I am interested in local Nusselt number over a distance L. So this will be nothing but local Nusselt number over a distance of x when x is considered L. So the formula will change to 0.332 into REL 0.5 into Prandtl number 0.333. So NUL will become 0.332. I have the value of REL. It is 1.480 into 10 to power 5 power 0.5 and Prandtl number is 0.696. I could remember this value. So after calculating this, the local Nusselt number over a distance of L will be so let me calculate this. So the Nusselt number comes out 113.20 local Nusselt number. So the average Nusselt number will be twice of 113.20. That means 226.44. So this is the value of average Nusselt number for a flow taking place over the length L of the plate. Let me confirm once again. Yes, this is the correct value. So now I can find out the value of average heat transfer coefficient from this relationship. So 226.44 is the average Nusselt number. I am interested in average convective heat transfer coefficient. The value of L is 1 and the value of Kf, that is thermal conductivity of the fluid, is 0.02896. 0.02896. So from here the value of H bar is the value for H bar comes out 6.56 watt per meter square degree Celsius. So this was our step number 8. So I could complete the step number 8. Step number 9, actually step number 8 was to find out the appropriate correlation for NU. Step number 9 was to calculate H bar and Q, and step number 10 was to calculate other parameters. So I have combined step number 8 and 9 and I got the value of Nusselt number and convective heat transfer coefficient H. Now let us calculate as per the requirement of the problem. So what it has been asked in the problem, we are supposed to calculate heat lost by the plate. So it is nothing but Q. The problem is asking to calculate heat transfer, and this is nothing but heat lost by convection. So we know heat transfer in convection can be calculated by Newton's law of cooling. So Q is equal to, which can be given as H bar into AS into Ts top minus T infinity. So Q will be 6.56. What will be surface area? This is the flat plate. Its length is L and its width is W. So this is the area over which flow is taking place. So this will be length into width. Length is 1 meter, width is 0.6 meter, top temperature is 90 and air temperature is 30. So the Q will be 235.90 watt. So this will be the answer of first part. The plate is losing 235.90 joule per second of heat from its top surface. Now the point number 2 is bottom temperature of the plate for the steady state conditions. Okay. So symbolically we are supposed to calculate Ts T suffix Sb. Now what is happening actually? First understand the physics of this problem. This is our plate and this is its bottom surface. The top surface temperature is TST, bottom temperature is TSB. Okay. Now heat transfer is taking place from plate to the air. So when heat transfer will take place from the top surface will lose some heat, and because of that top surface temperature will be lesser than the bottom surface temperature because of this physics. Because top surface is directly coming into contact with the air. Also, I am assuming that here heat transfer is taking place from top surface only. So because of this, top surface temperature will always be lesser than the bottom surface temperature, and direction of heat transfer will be from bottom to the top. And another thing, under steady state condition, now what is happening? The heat lost by this plate by conduction will be equal to heat lost by convection. So Q conduction will be equal to Q convection. And how can I write the expression for Q conduction? K, thermal conductivity of the plate, into area. Area normal to heat flow will be surface area of the plate actually, and temperature will be higher to lower. So TSB minus TS over thickness. See, if I draw the plate in this fashion, this will be the bottom temperature, this will be the top temperature. Heat transfer will take place in this direction, and heat transfer through this will be taking place by conduction, and this will be by convection. Got it? And we know that from Fourier's law of heat conduction, heat transfer rate through the plane slab can be given as Ka T1 minus T2 over L, where T1 is greater than T2. So all these the background behind this Fourier's law of heat conduction. So taking the Q from this, I could write the expression of heat transfer through this plate by conduction from Fourier's law of heat conduction as K, that is thermal conductivity of plate. Area normal to heat transfer will be this area. This will be the area normal to heat transfer, and this area is nothing but surface area. And thickness, so thickness in the direction of heat flow is H. So this will be H. This entire heat transfer rate by conduction will be equal to convective heat transfer under steady state condition. So let us put all the values. I know the value of Kp is given as, that is plate as 25 watt per meter degree Celsius. So 25 into surface area is 1 into 0.6. Ts bottom I have to calculate, Ts top is 90, and the thickness is 0.025. This will be equal to 235.90. So after simplification, you will get the bottom temperature as 90.39 degrees Celsius. So this way I could calculate the bottom temperature of the plate. So this way I can solve this problem. This is for plane slab.